So yeah, I'm going to be talking about water vapor trends in the stratosphere today. We were originally going to also look at the mesosphere, but that's someone else in our group's job now, so I'm just focusing on the stratosphere. And I thought I would start off today with just a one-slide presentation, so if you fall asleep after this slide, I won't judge you too harshly. But yes, so the basics. Water vapor in the stratosphere. So there are two main sources in the stratosphere. One of them is from methane oxidation, and then that's the secondary source. The primary source is you have this rising moisture-rich air from the troposphere coming up through the tropics. And then what happens as it's coming through that cold tropopause region, a lot of that water vapor gets freeze-dried and then gets removed and doesn't actually make it to the stratosphere. And so the stratosphere is relatively dry. However, since the early 2000s, it appears that the stratosphere, much like myself, has learned how to properly moisturize. And so it's actually getting more water vapor up there. And I mean, I do it for obvious reasons, but we're not exactly sure why the stratosphere is doing it. And so when we measure the basic trends, we don't do anything fancy. We're measuring water vapor trends. They're positive on the order of 2 to 5% per decade. Then if we account for dynamics, for methane oxidation, and for cold point any trends that might be in the cold point tropopause temperature record, we still get a positive, significant water vapor trend in the stratosphere throughout the stratosphere, lower stratosphere to upper stratosphere, and actually even in the mesosphere as well, on the order of about 1 to 3% per decade. And then this 1 to 3% per decade we haven't accounted for yet. And then at the end, if I still have time, I mean, it wouldn't be a modern water vapor talk without discussing Honga Tonga. So of course, we're going to be looking at Honga Tonga. Honga Tonga has made measuring water vapor trends a little more tricky because it just instantaneously added about 10% of the stratospheric budget. But we can still do it because we measure HDO, which was also lofted up, and so we can use HDO as a proxy in our linear regression model as well. And then that removes that signal from there. So those are the basics, and now I'll go into a little bit more detail. So first off, we're using ACE-FTS. Chris gave a very lovely talk on ACE-FTS earlier in the week, so I'm not going to go into too much detail, but it's on a Canadian satellite launched in 2003, has been making measurements since 2004, February 2004, measures in the infrared. It does exactly what your mother told you not to do. It stares directly at the sun. And because of this bright source, we are able to measure over 70 trace species in the atmosphere. You name your favorite childhood atmospheric species, we measure it. Unless it's bromine. If it's bromine, then you're crazy. Yeah, so we're using version 4.2 of the data. Version 5.0 came out late last year, so earlier than today. But yeah, so we're using 4.2 for this, and it spans February 2004 all the way up to April 2023, and we're still up there making measurements, so hopefully we'll be doing that for a while longer as well. I will also be showing some model data. The model that we used for this was CMAM, which is a Canadian model. If you're a sadist and you enjoy model specs, there's some in there. But basically, we've sampled the model at ACE-FTS measurement locations and just basically seeing what does the model say water vapor trends should look like as well if you were sampling at ACE locations. So the method that we're using here is MLR, so multiple linear regression, to derive the trends, and we do this with a few different regressors. So we do an annual cycle, semi-annual cycle, solar flux input. I didn't put it here, but obviously also a linear trend to get out the linear trends. For dynamics, we don't use any indices like QBO indices or anything, or ENSO or the kind of thing, because we measure N2O, which has a very long lifetime in the stratosphere and has all of those dynamics embedded in the data set itself. And we also use CO because it has a better signal up at the higher altitude. So we also use CO for as a dynamical tracer as well. And I guess I should point out, N2O itself has a surface trend because N2O is being emitted by us awful humans, and that's at about 2.8% per decade, and so we subtract that out before we use the N2O as the dynamical proxies. And then also we have a monthly mean tropical tropopause data set, which we have taken from a number of sources. 3 is that number. So we've got it from CMAM, also from MLS, and then we've also used ACE. And basically we've done nothing fancy with this record. We just go in, find the cold point tropopause temperature for all of these 3 data sets and just average them together. And that's what it looks like there in the plot. Might be a little bit hard to see. The blue is CMAM, the red is MLS, the yellow, which you can't see because we have fewer data points, many fewer data points, but it's also in there as well, contributing to that record. And as you can see, there's not really a trend in the cold point temperatures. So, some more on this. All right. So methane oxidation, you will notice, was not in those regressors. We can't use methane, which we do measure in the stratosphere, but we don't use that as a regressor because the water vapor doesn't depend on the methane that we measure. It depends on the methane that no longer exists. And so, because it was oxidized to make H2O, so their H2O and methane are anti-correlated. So if we were using methane, a positive trend in methane would give us a negative trend in water vapor, which is not the case. So there's a very simple equation for how you get methane, or how you get water vapor from methane. So it's basically just the amount of methane that entered the stratosphere minus the methane at your local measuring point times a factor. This factor is usually considered to be 2, but it is not exactly 2. And so what we can do to get the trend in H2O due to methane is take the trend, the measured trend at the entry point, and subtract the trend at the local point, and then multiply it by this factor that is nearly 2. And so we have done this. We measured the trend at 100 hectopascals between 10 degrees south, 10 degrees north, which is saying this is the entry point roughly. We assume that the trend is consistent throughout the time that we're measuring. And so we've got a trend there of 0.77 parts per million per decade. And then we can just subtract this from whatever we get in the regression. So that alpha term, just looked it up in a paper. It goes from, it's roughly 1.5 around 16 kilometers, and then 2 near the top, near the stratopause. And so we have done this for ACE FTS data and also with CMAM data, as I mentioned earlier. The CMAM data is linearly interpolated in time and then bilinearly interpolated to the ACE FTS geolocations at every altitude. So let's get into some of the results. So this on the left here is the water vapor trends that you would measure if you just fit to a linear function, to an annual oscillation, and a semi-annual oscillation. So nothing fancy. These are just the basic trends. This is what water vapor is doing when you don't account for dynamics or methane or anything like that. And so the scale goes from -5 to 5, but you'll notice there's no blue on here. It's all red. So it's all positive trends, basically. And then these shaded regions are where the trends are not significant to 95%. And so you can see there's this huge asymmetry between the hemispheres. And we believe this is due to dynamics because if you do the same multiple linear regression using the dynamics, so N2O and CO, and also temperature, but that's not dynamical, a lot of this asymmetry goes away and you're left with just this lovely pink rise of water vapor on the order of about 3% roughly throughout the stratosphere. And there is a little bit of an asymmetry between the hemispheres though still. But then, so that was just taking into account dynamics, but then if you account for methane oxidation as well and the lagged cold point temperatures, I guess, sorry, I didn't mention that before. So what we're actually lagging the cold point temperatures in the calculations. So basically we have this long record from like 1995 to present, and we just by brute force just lag that data set by a month. We do it for like multiple times and just get where we get the highest correlation with the fit, and then that's how much we lag the cold point temperatures by, whatever gives us the highest correlation between the measurements and the fit. And so when you do all of this, what you'll see is that these trends have decreased a little bit, but we still have significant trends on the order of 1 to 3% throughout the stratosphere. In the lower stratosphere, they're not as significant, and we have these little squares of insignificance throughout the lower stratosphere here as well. And then you can see how much we've had to lag the time or the cold point temperatures here as well. It's on the order of a few years. Okay, so this is what happens with the ACE trends. And yeah, we don't exactly know why there's still this trend. We don't know what is making water vapor increase. And so we went to the model, see, does the model think that water vapor should be increasing as well? And we see here that the model actually thinks it should be higher. There should be more of an increase in water vapor. So CMAM is showing about 2 to 6% increase per decade, even when you account for N2O, so for the dynamics and the cold point temperatures and for methane oxidation as well. So you count for all of that, model says, yeah, we should be seeing more water vapor. So the next step, which we haven't done yet, should be to go into the model and say, well, why does the model say it should be increasing? So, I mean, that's the natural next step, but we haven't done it yet. Well, one thing we were thinking about was, well, maybe it's due to what's happening closer to the surface. So I just did some quick things, downloaded some data, whatever I could find. So I downloaded some sea surface temperature data from MODIS and just wanted to calculate the trends from that. And we can see that in the tropical regions, sea surface temperatures have been increasing by about 1% per decade. So is that enough to produce 1 to 3% increase in water vapor in the stratosphere? Don't know. But the other thing we could look at is water vapor at the surface actually increasing or not? And so I downloaded some data from AIRS, and this plot on the left is the trend in total column water vapor. And so, because it's total column, it should be heavily weighted to near the surface. And I just want to pause for a second and just enjoy this. It's giving me coverage envy. I've been working with ACE for so long. It's like, you can get the trend at 0.5 degree latitude bins. That's I love it. Anyways, but they don't have the vertical, so there you go. But yeah, so there's spots where water vapor is increasing, spots where water vapor is decreasing. But if you get the zonal mean trends, this is what it looks like. And you can see, like, at the entry point, or in the tropics, water vapor is actually decreasing in the southern tropics, increasing in the northern. And then if you get the tropical mean, it's not even a significant trend. It's 0.2% per decade, plus minus 0.3% per decade. I mean, this was a very rushed calculation. I could have very easily done something wrong, but it seems like water vapor at the surface isn't increasing enough to explain why the stratosphere is increasing. So we have some work to do to explain this. So in terms of just measuring the absolute trends, that's all I had for that. And so it looks like I've got a bit more time. So we can look at the Honga-Tonga eruption and what ACE has been measuring since then. So as I'm sure you have all heard, Honga-Tonga was this submarine volcano that erupted and threw up a whole bunch of water vapor into the stratosphere directly near 25 kilometers. And you can see here this plume from the average of the plume in February to March in the tropics, southern tropics. You can see the plume there is much greater than this profile here, which is the 2005 to 2021 climatological mean. And so it's more than double even a few months after the eruption. And just did a quick estimate of how much water vapor. We agree very well with what MLS has been seeing. It's a roughly 10% increase. It's actually 14, we're measuring 14% increase in the stratospheric water vapor budget. So we're measuring 166 teragrams of water. And if you're wondering what the water plume looks like now, so in August, September, you can see water vapor didn't quite make it to the South Pole in time for the ozone hole. But then you can see in October, November, it starts getting into the southern polar regions. And then up into January, February, it's getting even higher up in the atmosphere near the equator, and then getting into the northern hemisphere and coming back down. You can see that March, April as well. And so this is percent deviation from the climatological mean. And so this is like still 50% higher, which is a crazy amount. And so you would think that this would have an impact on measuring trends. Of course, it does. But we can account for this because not only did Honga Tonga put up vast amounts of water vapor, it also had these isotopologues. So HDO was also thrown up at the same time as water vapor. And so there's a lot more HDO as well. And so that is an independent signal that we can use as a regressor in our trend calculations so that we don't have to just stop at January 2022. We can actually use HDO as that regressor, and then we can still get background water vapor trends, and we don't have to put a breakpoint in our trend calculation. And so with that, I think that is it. So basically, yeah, we're measuring trends of water vapor on the order of 2.2 to 5% per decade. When you account for everything, those trends are still there and significant on the order of 1 to 3% per decade. And so it looks like what's happening at the surface and in the lower troposphere is not enough to account for the remaining trends that we're still measuring. So the next step is to figure out what is causing those trends. And then, of course, Honga Tonga is a lot of fun. That is my talk, and so thank you very much.